So let us look at what the principle of mathematical induction is. So before going to mathematical induction, let us look at the meaning of the word statement. Statement or a mathematical statement. So we are dealing with statements in mathematics. So what is a mathematical statement? So mathematical statement is a sentence which is either true or false. There should not be any ambiguity. So a statement which is either true or false, I can confidently say that it is true or false, is called a mathematical statement. That is, if the statement can be something like this: sum of angles of any triangle is equal to 180 degrees. So this is a mathematical statement. So this statement can either be true or false. So if the sum of all the angles of all the triangles is equal to 180 degrees, then this statement will be true. If there exists any one triangle, at least one triangle, where the sum is not equal to 180 degrees, this statement can be thought of as a false statement. So this statement can either be a true statement or a false statement. So there should not be any ambiguity in the statement. Now there is something called an open statement or statement involving a variable. So statement involving a variable. Now if I say a statement, I have a statement P, so I can call this statement, I can give a name to this statement. Sum of angles of a triangle is equal to 180 is a statement. This can be called P. So P is a statement. Or Q is a statement, the sun rises in the east. That can be a statement. The statement can be the earth, the shape of the earth is a sphere. That can be a statement. So all this statement can be represented by some capital letters, can be assumed as some capital letters. So P is a statement. This is not a statement which involves a variable. This is a statement by itself. So now let us take a statement which involves a variable x. So a statement in x can be thought of as, so x plus 5 is equal to 6. So x plus 5 is equal to 6, and let us assume that this statement is defined on real numbers. So this statement P in a variable x is defined as x plus 5 is equal to 6, and it's given that this statement is defined on real numbers. Now if you take x as each real number, assume that if we take some real value of x, for any real value of x, we can check whether this statement is either true or false. So for a given real number, this statement might be true or might be false. So the set of values of x for which this statement is true is called the truth set of this statement. So truth set or solution set of this statement are the values of the variable for which this statement is true. So now this statement is true for, as you can see, for x is equal to 1. So the solution set or truth set of this P of x is the set of 1. So now let us take another statement. So let us take a statement in natural numbers n. So the statement in natural numbers n is, let us take the statement as 1 plus 2 plus 3 plus so on up to n is equal to n into n plus 1 by 2. So if I add consecutive natural numbers from 1 to n, the sum is equal to n into n plus 1 by 2. So this whole thing is a statement. The statement is not just this part or this part. This whole thing is a statement in n. So now what is the truth set of this statement? The truth set of this statement are the values of n for which this statement is true. So now if you want to check whether this statement is true for n is equal to 1, that is nothing but P of 1. P of 1 is the statement for n is equal to 1. So what happens to the LHS when n is equal to 1? So LHS will be 1 and RHS. So 1 is equal to 1 into 1 plus 1 by 2. So what is the statement correspond to n is equal to 1? 1 is equal to 2 by 2. So 1 is equal to 1. So this statement is true. So this statement is true for n is equal to 1. So now if I have to check whether the statement is true for n is equal to 2. So let us write the statement P of 2. So P of 2 is nothing but P of 2 is not a value. P of 2 is a statement. So 1 plus 2. So if you have n here, you have to go from 1 to n. So P of 2 is 1 plus 2 is equal to, so you have to put 2 on the RHS also, 2 into 3 by 2. So that is 1 plus 2, 3 is equal to 3, which is true. So similarly, if I have to check whether this statement is true for n is equal to 10. So P of 10 can be written as 1 plus 2 plus 3 plus so on up to 10 is equal to 10 into 10 plus 1 by 2. So you can add all the numbers from 1 to 10 and see whether, so this and this side are same. So if this side and this side are same, then P of 10 is true. Otherwise, P of 10 is false. So do you see the difference between a statement and an open statement? So a statement is a statement which will either be true or a false. Is a sentence which is either true or false. An open statement is a statement involving a variable, and an open statement is defined on some set of numbers, and in the set of numbers in which it is defined, the values of the variable for which the statement is true is called the truth set of the statement or solution set of the statement. And you have to see that the statement is not just a number. The statement is the complete sentence or the complete mathematical equation or inequation, whatever it is. So now let us try to see what the principle of mathematical induction is. So for example, let us take the statement P of n is 1 plus 2 plus 3 up to n is equal to n into n plus 1 by 2. So this whole thing is my statement P of n. So now if I ask you a question, so is this statement true for all natural numbers? So is this statement true for all natural numbers? So now if I have to answer that question, so what should I do? So first I'll check whether P of 1 is true, and then I'll check whether P of 2 is true, 3 is true, 4 is true, 5, 6, 7, till 100, till 1000, till 10,000. So if I go on checking this statement for each natural number, so that will be a never-ending process, because there are infinite number of natural numbers. If I have to check one by one, so I have to check for all infinite number of natural numbers. So that is not a good process to check the validity of this statement for all natural numbers. So if I have to check whether it is true for any particular natural number, then I can substitute the natural number and check the result. But if I have to prove that this is true for all natural numbers, that is, if I have to induct, that is, if I have to generalize this statement, so I cannot use it using deductive reasoning, that is particular. So I cannot go from particular results to general results. So for this type of questions, you have a principle of mathematical induction. So what does principle of mathematical induction say? So there are two principles of mathematical induction, the first and the second. So the first principle of mathematical induction. So for JEE mains, the first principle is sufficient. You don't need to go for the second principle. So the first principle says that, so if P of 1 is true, so if you have a statement P of n defined in natural numbers, so if P of 1 is true, that is, the statement is true for n is equal to 1, and if P of k is true, implies P of k plus 1 is true. If P of k is true, implies P of k plus 1 is true. That is, if P is true for any number, if you can prove that if P is true for any number, then it is also true for the next number, then the principle of mathematical induction says that P of n is true for all n belongs to natural numbers. So what does this principle of mathematical induction say? So if P of 1 is true, that is, the statement is true for n is equal to 1, and if the statement is true for P of k, if the statement is true for n is equal to k implies P of k plus 1 is true, then P of n is true for all n belongs to n. So this principle is very similar to the domino effect. So we know that what domino is. So you have plates like this, placed one after the other, and if you trip one of them, the whole domino will trip. So assume that, so I have tipped one of the domino. So I know that the first domino has been tipped, and I know that if a domino tips, it will tip the next domino also. So if I know these two statements to be true, that is, the first domino has been tipped, and if any domino has been tipped, then it will tip the next domino also. So can you say that all the dominoes will fall one after the other, because one has fallen, and from this statement, if one has fallen, two also should fall, and once two has fallen, if two falls, if I use this statement again, if 2 falls, 3 also has to fall, if 3 falls, 4 also has to fall, and this continues till infinity. So now, if you want to prove any result by mathematical induction, there are 4 steps. The first is, you have to prove that P of 1 is true. You have to prove P of 1 is true, or you have to verify P of 1 is true. Just need to verify that P of 1 is true. And second, you have an assumption step. You assume that P of k is true. This is an assumption step. So you assume that P of k is true, and you prove that P of k plus 1 is true. So you assume P of k as true and prove that P of k plus 1 is true. This is the proof step. So if you do all these 3 steps, then you can say that in the 4th step, you can conclude that P of n is true for all n belongs to natural numbers. So these are the 4 steps that you have in mathematical induction. First, you have to verify whether P of 1 is true. That is, if the statement is true for n is equal to 1. And then you assume that P of k is true. That is, the statement is true for some value of n which is equal to k. And from this assumption, you have to prove that P of k plus 1 is true. And if you have done this, then from principle of mathematical induction, you can say that P of n is true for all n belongs to natural numbers. So now, using this statement, let us try to prove some inductive statements.